This is the 14th lecture on DSP, and today we discuss discrete time systems in the frequency domain. We had introduced the topic in 13th lecture. We shall look at this very carefully today. In the previous lecture, we had continued our discussion on Z transform properties, and the properties that we specifically discussed in the last lecture were differentiation, which gives you a clue to finding the inverse transform of 1 minus alpha Z inverse to the power n, where n is greater than equal to 2. The differentiation property leads you to an inverse transform of this. We discussed the convolution property, that is, if you convolve g of n with h of n, linear convolution, then the Z transform of this is simply the product of g of z and h of z. Then we discussed modulation, that is gn times hn. What is the Z transform of this? And that is in terms of an integral containing a convolution of capital G and capital H, and a particular case of the modulation theorem in which small g and small h are identical to each other leads you to the Parseval's relationship for energy. We took several examples. One was to illustrate the fact that V star of n, the Z transform is capital V star of Z star, and the other one involved multiple poles, and we showed how to invert with multiple poles without differentiation. That is, you write a set of linear equations in the constants by putting specific values of z and then solve these linear equations, which is much simpler than differentiating and then putting the required value of z. We illustrated the importance of the signal e to the power j omega n, and we said that for an LTI system, e to the j omega n is an eigen function. An eigen function is any function such that when it is fed as the input to the system, the output is exactly the same function multiplied by a complex constant. In our case, this complex constant was the Fourier transform of h of n, that is, which we denoted by capital H of e to the j omega. Capital H of e to the j omega is a complex constant in such a manner that e to the j omega n fed to an LTI system whose impulse response is h of n is simply e to the j omega n multiplied by this constant, which I can write in terms of a magnitude and an angle. And therefore, if I know the response to e to the j omega n, then I know the response to cosine omega n and also sin omega n, because it is a linear system. If I take the real part of the left hand side, I must take the real part of the right hand side. Similarly goes for the imaginary parts. Therefore, this signal is an extremely important signal for linear time invariant systems. We illustrated the importance of this signal by considering the example of an m point moving average system, and we showed that the magnitude response can be very easily calculated. It is of the form sine divided by another sign, but in determining the phase one must be extremely careful to take care and take account of the sharp transitions in phase by an amount exactly equal to 180 degrees that occurs whenever the quantity, the real quantity ratio of signs changes sign, and therefore the phase that you get with an M point moving average system is piecewise linear. It is piecewise linear, that is, it's straight line up to a certain point, then there is a transition and then again linear and so on. This piecewise linear phase response and the ambiguity in phase response has to be remembered throughout your course on digital signal processing. This leads us to the concept of filtering. Once we have come to frequency response, definition of frequency response, now one can talk of filtering. A filter is an electrical device which selects the appropriate frequencies and rejects others. For example, an ideal low pass filter shall have a frequency response like this: capital H of e to the j omega. We are concerned with capital H of e to the j omega in discrete time systems. If we plot the magnitude, let me take a fresh page, the frequency response that we want for, let us say, an ideal low pass filter is that between some frequency 0 low pass and omega sub c, the magnitude should be ideally equal to 1. 1 is a normalized value, magnitudes remain constant at, let us say this is 1, and beyond omega sub c the magnitude should be equal to 0 up to our baseband is pi, up to pi. Then of course it extends on the other side also in the same manner, that is, what we want is, this is minus omega c and minus pi. Okay, this is our range of vision. We require negative frequencies as well as positive frequencies to make up a real signal, and j omega, e to the j omega, these are all contrived instruments to facilitate our analysis, design, synthesis, and making life simpler in general. Okay. Now this is an ideal low pass filter. This characteristic is that of an ideal LPF. Now an ideal low pass filter is not realizable due to a philosophical reason. Philosophical reason is nature abhors sharp transitions. People who are highly temperamental, they get angry very quickly. Human beings, the society does not like them. They moderate them, moderate them to an extent that they can be tolerated. Nature also, you have seen the sharp corners at intersections, for example. When the civil engineers make it, they are sharp corners, but after a while the cyclists, scooterists and the car owners, they make sure that it gets rounded off. All right. Now in the particular case under consideration, there are other more tractable and analytical reasons. One is that if I have a characteristic like this, its impulse response h of n is non-causal. That is, how do you find impulse response? 1 over 2 pi integral minus pi to pi capital H of e to the j omega, e to the j n omega d omega. That is the impulse response. The inversion of this, and if this is equal to 1, this is equal to 1 between minus omega c and plus omega c, then and the rest of it is 0, then you can replace this by 1 if I replace minus pi by minus omega c and plus pi by plus omega c, right. So, this is the range that we have to integrate, and the integration is very easily seen as h of n equal to 1 over 2 pi e to the power j n omega c divided by j n, not omega, we are integrating with respect to omega, minus e to the power minus j n omega c divided by j n. And you can see that this is simply equal to, if I combine, sine of n omega c divided by n pi, sine of n omega c divided by n pi. And obviously, when n equal to 0, this blows up, is it? No. At n equal to 0, it is 0 by 0 form, so it is omega c by pi. Okay. But this h of n obviously is not equal to 0 for n less than 0, it exists for n less than 0, and therefore, the system is non-causal and therefore not realizable. It is not realizable. On the, there is another reason why it cannot be realized. That reason is that the system, this h of n sine n omega c by n is neither absolutely summable nor square summable. In other words, the system is unstable. Well, instability does not require square summability, it only requires absolute summability. Summation h of n is not less than infinity, it blows up, it is not summable, and therefore, it is also unstable. Once at least in your life you should know why an ideal filter, this is true about ideal high pass, ideal band pass, ideal band stop, any ideal kind of filter, it is true that it is non-causal and also unstable, therefore, it cannot be realized. So, what we can realize for a low pass filter, for example, our range of vision fortunately in digital signal processing is 0 to pi. We have a finite range of vision, and when we are considering magnitude or phase, it suffices to consider only the positive frequencies, because we know for negative frequencies the magnitude is even and the angle is odd. Therefore, if we know this part, we know the other part also. Now, what we have, ideally we should have something like this, 0 to omega sub c. What we can have in practice is something like this, it has to be rounded off. So, we can have something like this, we can have something like this, okay, a smooth curve, and this is therefore an approximation to the low pass filter characteristic. We can have other kinds of characteristic also. For example, the the characteristic here within this rectangle does not have to be monotonic, it can have ripples, it can go up and down. Similarly, in the band in which you do not require any frequencies, it does not have to be monotonic, it can also go up and down. But the simplest of course is this, that is the characteristic. Which characteristic? The magnitude. We are not considering phase. The magnitude characteristic, simplest is that it is monotonic in the monotonic throughout. Now, we now have to define, you see, if it is an ideal characteristic, then omega sub c is the cutoff frequency. We now have to define, so we define a cutoff frequency as the frequency within which the magnitude does not fall below, let us say, some quantity alpha. Omega c, the cutoff frequency, is defined as magnitude h lies between alpha and 1, 0 less than equal to omega less than equal to omega sub c. This is the cutoff frequency, and alpha traditionally is 0.707 or 1 by root 2, because 20 log 10 1 by root 2 is minus 3, and the usual parameter, usual characterization that we take is 3 decibel cutoff. That is 20 log 10 of 1 is 0. So, this is 0 dB point, and up to the frequency at which the magnitude response does not fall by more than 3 decibel. So, this is the 3 dB band width of the low pass filter. The width of the band within which the magnitude response does not deviate by more than 3 decibel is the 3 dB bandwidth. Ideally, we should have had 0 decibel, that is unity transmission. Okay. So, this range is called the pass band, and then you have to define a stop band, that is, ideally the pass band is 0 to omega c and the stop band is omega c to pi. However, omega c to pi we cannot have 0 response for this extended range. What we could have is 0 response at some isolated points if we allowed ripples, but in a monotonic response we have to define another constant beta and the edge of a stop band omega s, such that between omega s and pi the magnitude response does not go beyond beta. Beta, for example, if beta is, let us say, 0.001 10 to the minus 3, then in decibel it corresponds to 60 decibels down. 20 log 10 of 10 to the minus 3 is minus 60. So, typically what you shall be specified is that in the stop band the attenuation must be at least 60 dB. Okay. If it is at least 60 dB, then your beta is 0.001. Omega s shall also be specified. For example, if it is a speech filter for digital telephony, you might specify omega c to correspond to, omega c is a normalized digital frequency, omega c may correspond to 3.3 kilohertz. Omega s may correspond to 4 kilohertz, 4 to 20 kilohertz, pi should correspond to the end of the audio band, 20 kilohertz, and this band omega s to pi is called the stop band. That is, whatever may happen elsewhere within the stop band, the signal must be attenuated by at least the amount specified. It could be 60 dB, it could be 80 dB. The in between region, which unfortunately is a fact of life, that is between omega c and omega s, it has to be permitted, because from omega c it cannot come to beta immediately, it cannot make a abrupt jump. If it does, then again non-causality shall step in. Nature abhors sharp transitions. Okay. So, you must allow a region, and this region is called the transition region, transition between pass band and stop band, transition region. The narrower the transition region, the better is the filtering. Okay. Transition region sometimes is also specified by the cutoff slope, that is, if you find the slope at this cutoff point, this is also an indication of how sharp the filtering is. The more the transition, the more the cutoff slope, the better is the rejection of unwanted frequencies. So, a filter, a digital filter in practice, digital or analog, it does not matter, shall have a pass band, shall have a transition band, and shall have a stop band. What typically you shall be specified is the bandwidth of the pass band, the pass band tolerance. It could be, there is nothing sacred about 3 dB, it could be 1 dB. In a more sophisticated situation, it could be 0.1 dB, all right. Similarly, you shall be specified the stop band and the minimum attenuation in the stop band. If you over satisfy the stop band, you are perfectly all right, you are a good boy or girl, but but the transition region is a fact of life, it has to be tolerated. The narrower the transition region, the better is the filter, but then you have also to pay for any improvement that you desire. That is, sharper cutoff requires higher order of filtering. Higher order means more cost, more hardware, more software, and therefore more cost. This is the concept of filtering. To illustrate the concept of filtering, let us take an example. Suppose you have a suppose you have an x of n which contains two sinusoids, a cosine, let us say omega 1 n plus b cosine omega 2 n. There are two sinusoids in the signal. The frequencies are omega 1 and omega 2. The signal x of n is not necessarily periodic. Is that correct? It is not. Digital signal, even if it is a sine or cosine representation, is not necessarily periodic. For periodicity, omega 1 by 2 pi must be a rational number. Similarly, omega 2 pi must be a rational number, and the denominators of omega 1 and omega 2 must have, if they are periodic, then the periodicity of the sum is the LCM. Okay, you know how to do this. Now, suppose we have two signals and we want to pass omega 1 and reject omega 2. That is, the condition should be that 0 omega 1 is greater than 0, but it is less than omega c, then omega c must be less than omega 2, which is less than pi, right. This specifies that it is a low pass filter. 0 to omega c is our pass band, so omega 1 lies there. Omega 2 is greater than omega c. It could be in the transition band or in the stop band. Now, we can design filters such that the transmission at omega 2, you see, what would be y of n if I feed this signal to a linear time invariant system? What would be y of n? The magnitude would be modified by h of e to the power j omega 1, agreed, and the phase would be modified by cosine omega 1 n plus some angle h of e to the j omega 1. Is this clear? You see how we are writing the response? All we have to do is to find the frequency response of the system, capital H of e to the j omega, then the output we can write directly. Cosine omega 1 n shall be affected in magnitude by magnitude of h at omega equal to omega 1, and its angle shall be shifted by this amount, plus b similarly magnitude h of e to the j omega 2 cosine of omega 2 n plus angle of h e to the j omega 2. All right. All that I have to find now, we have to choose the system in such a manner that h of e to the j omega 1 should be approximately equal to 1. Ideally, I can also make it 1. Okay. And magnitude h of e to the j omega 2 should be approximately equal to 0. Then I have done low pass filtering. All right. Let us take a specific example, and to bring variety into experience, let us say we require a high pass filter. Let us say x of n is equal to capital A and capital B are constants, we need not bother about them. Let us say we have a 0.1 n plus cosine of 0.4 n. Is this signal periodic? Yes? Is this signal periodic? No, not at all. 0.1 divided by twice pi can never be a rational number, because pi is an irrational number. So, it is not a periodic signal, but we want to retain, this is to be retained. And this is to be rejected. Okay. So, what we want is that capital H of e to the j 0.1 n should be equal to 0. Why not make an effort to make it equal to 0, and capital H of e to the j 0.4 n should be equal to 1. Let us see if we can satisfy this. Okay. Let us design the simplest possible kind of filter to satisfy this. And the filter that we aim at, let this be, to start with, let it be FIR, finite impulse response, of length 3 arbitrarily. I could also choose length 2. Let us say we have length 3, and let us suppose that my h of n is equal to alpha, beta and alpha. This is n equal to 0. Let us see, you see, I require 2 degrees of freedom. I require 2 constants which are to be adjusted to satisfy the 2 conditions. That is, at 0.1 the magnitude should be equal to 0, at 0.4 the magnitude should be equal to 1. That is why I chose 2 constants here, and therefore capital H of e to the j omega, which is the Fourier transform of this, I can very easily write as alpha plus beta e to the j omega plus alpha e to the minus j 2 omega, which if I take e to the minus j omega out becomes beta plus twice alpha cosine of omega. Agreed? Is that okay? E to the minus j omega, not beta. Yes, thank you. Now, it is very easy, it is very tempting now to say that the magnitude of H must be this quantity. No, not necessarily. This part is real, but it does not mean that it cannot go negative. It can be positive as well as negative. This is a step where you can falter throughout your journey of digital signal processing. Whenever a real quantity is given, it can be positive as well as negative. Both have to be respected. The negative sign has to be respected by including an angle of pi in the angle. So, the angle of capital H is minus omega as long as this quantity is positive, and it is minus omega plus pi whenever the quantity changes from positive to negative. That is, whenever it becomes 0, there is a transition of phase by an amount pi. Now, let us suppose that we aim at beta and alpha in such a manner that this quantity shall remain positive. What are the, if the final result does not justify this, then we will go back, all right. This is the engineer's way. It does not quite start with rigorous mathematical formulation and so on, because then he gets lost in the mathematics. You have to keep your eyes towards practical situation. So, what I want is 2 alpha cosine of 0.1 should be equal to 0, all right, and beta plus 2 alpha cosine of 0.4 should be equal to 1. And it turns out that you can subtract the one from the other and find alpha very easily. Now, cosine of 0.1, cosine of 0.4 can be found out from the tables. This 0.1 is in radians, okay, and therefore one finds that alpha, by solving this, one finds alpha equal to minus 6.76195 and beta equal to 17.4563335. With these values, you can verify that beta plus 2 alpha cosine omega remains positive between 0.1 and 0.4. That is all that we are concerned with. It remains positive. Okay. Now, yes.
What is the criteria for deciding the accuracy of this particular?
What is the criteria? Oh, how did we, is the question, how did we fix 3 length?
How did we say that, okay, the first number may be still longer, 6.761957?
Oh, how did we decide on this? It's a 5 and here is 6. No, I think I have done it arbitrarily. It depends on how many bits are required to represent it. If you see, it's the other way around. You have to, what is it called? If you have a limited amount of cloth, okay, then you have to decide how many shards can be made out of it, or how many pieces of dress. Okay. So, if you have either an 8-bit or 16-bit hardware, okay, or your computer, if it is a software, let us say you can go up to 32-bit. So, you decide the number, the precision which can be represented by as many bits. Okay. For example, if it is an 8-bit number, you should not truncate after the first decimal. Okay. On the other hand, if it is a representation in floating point, then you can use more decimals. Okay. So, it is decided by the amount of money that we wish to spend, okay, amount of investment. Now, obviously, after you have found out alpha and beta, the system is now known. What would be its difference equation, for example? Y of n, you remember, y of n shall be alpha x of n, h n is alpha, beta and alpha, that is all. So, y of n shall be alpha x n plus beta x of n minus 1 plus alpha x of n minus 2, as simple as that. You can implement this with 2 multipliers only, because x n and x n minus 2 can be added together, then multiplied by alpha. Reducing the number of multipliers is an extremely important criterion in the realization of a DSP. Now, in general, if the processor is not FIR, it is IIR, then you know it can be written down in the form of a difference equation like this: y of n, let us say, equal to let us say plus b1 y of n minus 1 plus etc. plus b n y of n minus n, let us say, is equal to x of n, let us say a0 x of n plus a1 x of n minus 1 plus etc. a capital M x of n minus capital M. This is the general representation of an LTI discrete time system. It can be FIR, it can be IIR, but the most general representation is this, and then you can write the frequency response capital H of e to the j omega. If you take the Fourier transform of the left hand side and the Fourier transform of the right hand side, then you can write this as a0 plus a1 e to the minus j omega and so on, plus am e to the minus j omega m divided by b0 is 1, all right. This is a discipline that we have tried to inculcate. b0 is 1 plus, if there was a b0 we would have divided by b0 also. So, we make the coefficient of yn as equal to 1. So, 1 plus b1 e to the minus j omega plus etc. plus bn e to the minus j omega n. This is in general the form of the frequency response, and in general it represents an IIR system. There is no reason why it cannot represent an FIR system also, because there may be pole 0 cancellation. Okay. This can now be generalized to in terms of Z transforms. So far we have considered representation of the discrete time system in the omega domain by taking Fourier transform. There is no reason why you cannot Z transform and generalized capital H to capital H of Z. That is, instead of taking the Fourier transform, we can also take Z transform, provided the Z transform exists. Okay. And H of Z can now be written as a0 plus a1 Z inverse plus etc. So, it would be in general be of the form pz by qz. It would in general be of the form of a rational function which is a ratio of polynomials in Z inverse. When we talk of H of e to the j omega, suppose we want to find out the frequency response of this, then Z will simply put as e to the j omega, provided the ROC of this includes the unit circle. If not, then we cannot do it. Okay. Fortunately, most of the systems that are of our interest can be treated by both Z transforms and Fourier transform. However, there is a change in nomenclature. This we call the frequency response. Now, we have to give, why it is called frequency response? Because this gives the spectrum in terms of actual omegas. On the other hand, we must give a name to this. This is simply called the transfer function. Because as you can see, it is also the ratio of y of z divided by x of z. How x of z is transferred to the output is characterized by the ratio h of z, and one should remember that the z domain transfer function and the frequency response are intimately related, provided both of them exist. As an example, if we take the m point moving average system, that is y of n is equal to 1 over m summation x of n minus k, where k goes from 0 to capital M minus 1. Agreed? What is the impulse response of the system? It is 1 by m for n going from 0 to m minus 1, otherwise it is 0, and therefore you can take the Z transform and find that h of z is nothing but 1 over m z to the power minus n, where n goes from 0 to capital M minus 1. This is the Z transform, and this is geometric series. The Z transform exists because the summation is finite. Summation is finite. So, it is 1 by m 1 minus z to the minus m divided by C inverse. It is a rational function, but it represents an FIR system, because the pole at z equal to 1 cancels with the 0 at z equal to 1, right. The zeros of this system, capital M number of zeros at z equal to e to the j 2 pi k divided by m. These are the zeros. Agreed? Z to the m is equal to 1 and 1 is e to the j 2 pi k. So, these are the zeros z k, k equal to 0 to m minus 1. The pole, just one pole at z equal to 1, and you notice that k equal to 0 gives z equal to 1. So, there is a pole 0 cancellation and the system is still FIR. To determine the frequency response, which you have already done and discussed, you just put z equal to e to the j omega, z equal to e to the j omega, and then put it in the form of sine by sine and an angle and carry out the rest of it. Now, when you express the transfer function as let us say p of z by q of z, the zeros of q of z are of course the poles of the system, and the zeros of p of z are the zeros of the system, and you know how we represent them in the z plane by means of crosses and small circles. But the important point is that if qi is one of the poles, then the magnitude of qi must be bounded by unity. Magnitude must be bounded by unity. What is the logic? Because the impulse response will be of the form qi to the power n u of n, and if qi magnitude is not bounded by unity, then it grows without limit. So, it becomes an unstable system. Not that unstable systems are not useful, okay. Unstable systems we require for oscillation. If you want to make a digital oscillator, then we do require an unstable system, but not for any other purposes, okay. So, qi, the poles must be inside the unit circle. It is a repetition of what we had done, what we had stated earlier. Now, we continue our discussion on filtering and take some very simple examples of filters. First, we consider some FIR filters, simple digital filters. First, we consider the FIR category. It is much simpler to consider rather than IIR. And let us consider first a function like half 1 plus z inverse. Any FIR system will be a filter. Any system which has a frequency response will favor some and reject others. So, it is a filter. What kind of filter is this? The way to do it is look at the function and mentally you know that z is e to the j omega when you consider the frequency response. Well, let us for one or two examples let us write this down. Later on we will not 1 plus e to the minus j omega. and you see this is equal to, at omega equal to 0 it is equal to 1, and at omega equal to pi it is 0, and therefore it is a low pass filter. It starts at 1 at omega equal to 0 and goes to 0 at omega equal to pi. Now, in order to decide whether it is a low pass or high pass or any other kind of filter, later on this step will not be required, because omega equal to 0 corresponds to z equal to 1. Isn't that right? Omega equal to pi corresponds to z equal to minus 1. So, you just have to find out plus 1 and minus 1. Suppose both of them are 0, then you know that in between there must be a maximum, so it must be a bandpass filter. Agree? We will come to bandpass case later. But then this low pass example, half 1 plus z inverse, if you write the frequency response, obviously you can write h of e to the j omega as equal to e to the minus j omega by 2 cosine of omega by 2. Is that right? I am avoiding the intermediate algebra. Put z equal to e to the j omega, take e to the minus j omega by 2 out, then this is what it is. Now, cosine of omega by 2 in the range 0 to pi is positive. Agreed? So, if I plot the magnitude, it starts from 1 and at pi it goes to 0. So, the characteristic would be something like this, which is indeed a low pass filter. Okay. And the angle, if I plot the angle phi 0 and pi, the angle will be strictly minus omega by 2. So, it start from 0 and go to minus pi by 2 at omega equal to pi. It's very simple. In the range of vision, the real quantity does not change sign. So, we are comfortable. Okay. Now, if this is a low pass filter and let us say 3 dB cutoff, we want to find out omega c, then what we want is cosine of omega c by 2 should be equal to 1 by root 2. Agreed? And obviously omega c is equal to pi by 2. Cosine of pi by 4 is 1 by root 2. So, exactly halfway between them. It is a very lousy, it is a very bad low pass filter, large bandwidth and large stop band and so on. Okay. It is not a very good one, but it is the elementary, most elementary FIR low pass filter. If you want to sharpen the characteristic, if you want to make it a better, for example, if you want to make it like this, okay, obviously since all these values are less than 1, if I square a quantity less than 1, let us say 0.9, then the square will be 0.81, so it will come down. Isn't that right? If the stop band attenuation somewhere is 0.1 squared is 0.01. Therefore, by cascading such filters, I can get better characteristic. For example, if m number of such HZs are cascaded, then where would be the omega c? What would be the cutoff frequency? This to the power m, agreed? That is the magnitude of one of them. So, to the power m should be equal to 1 over root 2. So, omega c shall now be equal to 2 to the power minus m by 2 cosine inverse. Do you see what I am doing? mth root on both sides, 2 to the minus m by 2, then cosine inverse cosine 2. This is approximately equal to 0.3 if m is equal to 3. 3 such sections. So, the cutoff frequency comes closer, in other words we get a better filter. This is the way people still design. People who do not know digital signal processing, who have not taken a formal course and so on, they want to just design a filter. Biomedical signal processing, for example, half 1 plus Z inverse is a very sacred filter to them. If one does not work, you cascade a number of them and get it done. Now, if I change the sign, half 1 minus Z inverse, without going through any Fourier transform, you can tell me what this filter is. High pass, because H of 1 is 0 and H of minus 1 is equal to 1. So, it is a high pass filter. You can also show that H of e to the j omega is equal to j times e to the minus j omega by 2. Where does this j come? Because we want to make this sine of omega by 2. Sine requires a j. You can put z equal e to the j omega and make simplification like this. And the magnitude obviously is the magnitude of sine omega by 2, which does not change sign in the range 0 to pi. Therefore, the magnitude of H, you have to go only up to pi, it goes like this, high pass filter, and you can show that omega c, that is the 3 dB cutoff, is once again pi by 2. Very easy. But what about the phase now? Phase at omega equal to 0, this does not contribute phase, but this term j contributes a phase of pi by 2, and beyond omega equal to 0 the phase will be pi by 2 minus omega by 2. So, it comes linearly down to 0, linearly down to 0. Okay. One fact of great importance is the following, that H of z equal to half 1 plus z inverse was a low pass filter, but 1 minus z inverse is a high pass filter, and this is in general true. That is, given a low pass filter, given H L P of z, you can always derive a high pass filter H P of z if you change z to minus z, if you change z to minus z, okay, it will become a high pass filter. And the logic is not difficult to find. You see, z corresponds to e to the j omega, minus z corresponds to e to the power j omega minus or plus pi. Let us write omega minus pi, which means that whatever occurs at omega shall now occur at omega equal to pi. All right. The magnitude was 1 for the low pass filter at omega equal to 0. Now, the magnitude will be 1 at omega equal to pi. So, the characteristic is just flipped over, all right, and this is in general true, that in any low pass filter, if you change z to minus z, then you shall get a high pass filter. In terms of an FIR filter, for example, suppose the low pass filter is A0 plus A1 z inverse plus etc. plus an z to the minus n. Suppose this is the story, then all that you are doing, changing z to z in minus z, is also equivalent to changing the sign of alternate coefficients. Isn't that right? The coefficient of z to the minus 2 remains A2, but the coefficient of z to the minus 1 becomes minus A1. So, it is also said that if alternate coefficients, the sign is changed, which means that you modify the impulse response such that alternate samples are made negative, then you get a high pass filter. So, it is a very simple low pass to high pass transformation. The characteristics are complementary. The cutoff frequency remains the same. The cutoff frequency remains the same. Is that correct? They would obey omega c and omega c minus pi or pi minus omega c. All right. Does it remain symmetrical? Not necessarily. Okay. For the simple case 1 plus z inverse, 1 minus z inverse, they remained identical, but it is not necessarily true. One should remember this. Now, the next thing I am asking for is a bandpass filter. What I want is a characteristic like this. At pi it should be 0, at 0 it should be 0, and somewhere in between it should be 1. Okay? Obviously, one of the very simple things that I can do is to cascade a low pass with a high pass. That is, if I have 1 plus z inverse and 1 minus z inverse, shall I multiply by 1/4 or half? We will see what the multiplication is. Suppose I take a function like this, then obviously at omega equal to 0, that is z equal to 1 it is 0, z equal to minus 1 it is also 0, and where does the maximum occur? For that we have to write this as 1 minus z to the minus 2, and therefore h of e to the j omega shall be equal to a e to the minus j omega multiplied by cosine of, yes, cosine or sine? Sine. Then I must multiply by j, sine of omega, and obviously this frequency shall be, sine omega is a maximum at pi by 2, so this shall be pi by 2. Agreed? It is a simple band pass filter. All we have simulated is sine omega. Now we shall have to be careful with the phase. Okay? We shall have to be careful with the phase. Sine omega, does it remain positive between 0 and pi? Yes. Yes, then you do not have to be. But this 90 degrees you have to take care. Okay. What are they going to say? What do I do if I want a band stop filter? But before that, can you tell me what its bandwidth shall be? Pi by 2, so you require, it shall also be pi by 2. Bandwidth is the difference between the two frequencies at which the magnitude is 1 by root 2. Bandwidth is also pi by 2. It is a poor band pass filter, nevertheless it is a band pass filter. Suppose I wanted a band stop, then what should I do? Pardon me? High pass and
Plus,
high pass plus low pass.
plus in the sense parallel.
All pass minus band pass would be a band stop. Yes, we will use this. We will use this. But tell me the simplest. Instead of sine omega, if I had cosine omega, then I have done the job. Cosine of 90 is 0, cosine 0 is plus 1, and cosine pi is minus 1. Agreed? So my h of z, oh, you did not tell me what this capital A should be. Capital A should be half, not 1/4. Isn't that right? I have made a mistake here, this is not correct. This should have been twice A. So capital A equal to half will give me response 1. In a similar manner, you can show that if I take half 1 plus z to the minus 2 instead of minus e to the minus 2, then I get a band stop filter, and that is the correct point to stop.